namely solutions that that are independent of the spatial coordinates and depend only on time. And to lowest order in alpha prime by Meissner and Veneziano, and then shortly thereafter, it was proven that this symmetry extends to all orders in alpha prime by Sen. Roughly, it follows from the fact that the internal coordinates, the left and right movers of the string, have a separate OD symmetry. So you get an OD times OD symmetry, which then gets enhanced by regular symmetries to OD, D. Many integrable deformations can be realized, in fact, using this ODD symmetry, but I have to apologize that I won't be talking about integrability or deformations today. I will only be talking about the middle word here, dualities. So today, I would just be interested in how we can use this ODD duality symmetry to learn about higher derivative corrections, alpha prime corrections to the string effective action. Okay, so the tree-level string effective action looks like this. So you have first this factor of e to the minus twice the dilaton, because we're at tree level, and I'm dropping all the higher G string corrections. But then you have an expansion, the rest of the Lagrangian can be expanded in powers of alpha prime, an infinite series of terms. At lowest order, we have the familiar usual supergravity. If I restrict to just the NS and S sector, which I will mostly do, which is the sector that's common to all the string theories, it looks like this, L0. H, as usual, is the field strength of the B field. And the dimension, for the case of the bosonic string, is 26, and for the superstrings, it's 10. And then we are interested in the first few of these alpha prime corrections, and they're known, at least their schematic form is known to be the following. So the first correction at order alpha prime exists for the bosonic string and the heterotic string, and it involves the Riemann tensor squared plus some other stuff, which we won't need here. So schematically, it's just the Riemann tensor squared. At the second order in alpha prime, again, both the bosonic and the heterotic string have a correction. For the bosonic string, it involves now the Riemann tensor cubed, while for the heterotic string, there's no Riemann tensor cubed, but there's some Lorentz-Chern-Simons term cubed instead. Okay, the precise form will not be very important. Then there are also other terms which involve in particular the H field. And then what's most interesting for this talk is the correction at third order in alpha prime. And it involves, not too surprisingly, the Riemann tensor to the fourth power. And this correction is present for all the string theories. So for the bosonic, the heterotic, and the type 2 theory. So the maximally supersymmetric type 2 theories, their first correction appears at this order, alpha prime cubed. And you see this funny coefficient, Zeta of 3, that appears, that multiplies this correction at order alpha prime cubed. And that coefficient doesn't appear in these lower corrections. I should say also that actually for the bosonic string, there are also quartic Riemann terms which don't have this Zeta 3 coefficients, but they will not play much of a role in my talk. Now, the first two corrections are completely known. So all the terms are known, including the ones that I didn't write out, while the third order correction in alpha prime is not fully known. And the question I want to ask here is if we can use the ODD symmetry that has to be there to determine the form of these corrections, which would be most interesting, of course, for the L3, which is not fully known. Of course, the traditional way to determine these corrections is to compute scattering amplitudes. The required scattering amplitudes have been pretty much computed, but then there's a lot of work involved to go from the amplitude to a local effective action. So, but that's one way to do it, but it hasn't been done fully. Now, if you want to use ODD instead to compute these corrections, maybe the most straightforward approach is to just start from an ansatz for the 10-dimensional action at the order of alpha prime that you're interested in. And then you reduce it to 10 minus d dimensions, and you demand that the result should be invariant under ODD. Okay, that's the basic idea, and that's the most straightforward thing that you can do. But it turns out to be quite complicated. But it has actually been done for the case where d is 1. So that means reduction of one dimension, a circle reduction, if you want. It's been done up to and including order alpha prime cubed in a series of papers by Garuzzi. And the result is that T-duality, in this case, it's just ordinary T-duality on a circle. It completely fixes the NS and S couplings up to the overall coefficient. So that was shown at order alpha prime cubed late last year. But the disadvantage of that approach is that you have to deal with a very large number of terms. So basically you have to do it on a computer. For example, for alpha prime cubed, he has to start from an ansatz in 10 dimensions, which has around 900, a basis of about 900 terms. And then you have to reduce those and demand T-duality invariance. And in the end, you end up with some result, but it consists of hundreds of terms, and it's very hard to see any structure in the result. I think it's about 200 terms or over 200 terms in the end result. But nevertheless, it's important because it establishes that the T-duality completely fixes the form of this invariance, at least up to alpha prime cubed. Okay, and the other possibility, which we heard a lot about this morning, is to do a cosmological reduction where you reduce on 9 dimensions. So you end up with the fields just depending on time. There it's much simpler because it's simple to deal with the theory where the fields depend only on time. But you don't have enough terms to fully fix the form of the 10-dimensional Lagrangian. But this was studied recently, actually, in 2 papers, one by the Holman Company and another paper by David and Liu that appeared a couple of weeks ago. Now, the difficulty in doing this appears basically because ODD is not a normal symmetry because it appears only on dimensional reduction. But if it was possible to circumvent this somehow and to formulate the theory in 10 dimensions already, so that this symmetry was obvious already there, then you would have then it would be much easier to use it to determine the form of these corrections. So in particular, if you could have a theory that had O10-10 symmetry in 10 dimensions, or O26-26 in 26 dimensions for the bosonic string, if you could formulate the string theory, the low energy effective action of the string in such a way, then it would automatically give rise to ODD on reduction. So in that sense, it would make the T-duality manifest. And the attempt to formulate the string effective action in this way with this bigger symmetry before dimensional reduction is known as double field theory. And it started really with work of Siegel, although it goes back, I mean, many of the ideas go back to early work by Duff and Zeitlin in 1990. And then it was taken up again by Holm, Hull, and Sweepak around 09, 010. Now, the name double field theory comes from the fact that this ODD, or O10-10, if we take the superstring case, has to act on the coordinates. And that means that you need to double the number of coordinates that you have from D to 2D. So from 10 dimensions, you have to go to 20 dimensions. So we have to replace our coordinates with this lowercase x by this big X with the capital M index, which runs over 2 sets of coordinates, the usual ones, X with an upper index, and then X tilde with the lower index, which we call, which is sometimes called the dual coordinates. And now the point of this is that now this big X can transform as a vector under OD comma D. It's in this way, where this ODD matrix by definition preserves the ODD metric, which we encountered also in Olaf's talk this morning. And because of the split symmetry, you can write it as ones off the diagonal. But we don't want to describe a 20-dimensional theory. We want to describe the original 10-dimensional theory. And the way to do that is to impose an O10-10 invariant constraint, which halves the dimension. And the constraint that's typically used is what's called a section condition, or sometimes also called a strong constraint. And it says that for any two fields in the theory, phi1 and phi2, if we have a set of contracted derivatives, and the derivatives here with the capital index are contracted, this capital index M is contracted with the ODD metric eta, then that should be 0. Now, if we write this out using the fact that this ODD metric is off diagonal, we see that because of that, one of the derivatives is acting on along the x coordinates. One is a derivative with respect to the, with respect to the coordinate x, and one is a derivative with respect to the coordinate x tilde, just because this is off diagonal, or the other way around. So that means that there's a standard way to solve this constraint, which is just to declare that all the fields should depend only on x and not on x tilde. Then obviously these tilde derivatives give you 0, and you've solved this constraint. And you're back to a 10-dimensional theory where your fields depend only on the coordinates and not the dual coordinates. So that's the solution that we will assume here in the cases when we deal with double field theory. Now, it's important to stress that a priori such an ODD or O1010 invariant formalism, before you dimensionally reduce, is not guaranteed to exist. But nevertheless, it was shown in some of those papers that I referred to earlier, that it is possible at the lowest order in alpha prime at least to cast the action in an O1010 or O2626 invariant form. But even more remarkably, Marcus and Nunez showed that you can also write the first alpha prime correction, which, as you remember, there's a correction both for the bosonic and the heterotic string, and they're slightly different. They both involve the Riemann square. But in both cases, you can write that correction also in an O1010 invariant form, or 2626 or 1010, depending on which case you're in. Okay, so it works to lowest order and it works to first order in alpha prime. And in fact, the way that it works to first order is sort of interesting. And it's related to what Olaf was talking about also. So in the formulation of double field theory that Marcus and Nunez used, which is known as a frame-like formulation, this correction arises as a Green-Schwarz-like correction to the double Lorentz transformations, which is sort of what replaces the ODD transformations in that context. But once you correct those transformations, because of closure that of the transformation, that implies also higher order corrections. So there will be corrections to alpha prime squared and so on. There'll be an infinite tower of corrections. And in fact, the corrections at order alpha prime squared, their form has been determined in double field theory language, so it hasn't just been matched to what is known, but they appear to have the right structure to fit with the alpha prime squared corrections, both for the heterotic and the bosonic string. And remember, they're slightly different. The bosonic string has a Riemann cubed term, while the heterotic doesn't. But there's actually two parameters involved in this Green-Schwarz-like modification, which allows you to account for both. Okay, so that seems very promising, but you can immediately see that it cannot account for the alpha prime cube correction. And that's because of this coefficient state of 3 that we mentioned. There's no way to generate state of 3 just by completing something that's just proportional to alpha prime. Right? You can never generate a state of 3 that way. So that has to be some independent correction. It can't arise in the same way. And indeed, in some work with my student, we showed that these terms, the Riemann to the 4th terms proportional to theta 3, don't seem to be compatible with O1010 symmetry, at least with the mild assumptions that we had to make. Okay, so to understand a little bit better what the problem is in trying to write these in an O1010 invariant form, I have to introduce a little bit of double field theory in this formulation that was used by Marcus and Nunez, which is usually referred to as the flux formulation. And it was introduced originally by these guys. So in that, it's as we said, a frame-like formulation. So you start from a frame field or a generalized field bind, which you parameterize in this way. So B is the usual B field. And then we have this E plus and E minus, which are two sets of ordinary field lines for the same metric, the standard metric G. So we just introduced two sets of field lines for the metric G. And the point is now that because we have introduced two of them, we can allow them to transform independently under two copies of the Lorentz group. So we're doubling the Lorentz group, and E plus transforms under one copy with parameters lambda plus, and the other E minus transforms under the other copy of the Lorentz group. So that's the double Lorentz symmetry. And in this framework, there are two metrics that are actually constant metrics. One is the ODD metric, which we had before, but if we rewrite it in terms of these A indices by translating the M to A indices using the generalized field line, it becomes diagonal instead of diagonal, but it just becomes the Minkowski metric and minus the Minkowski metric on the diagonal. Then there's another metric, which is also constant, which is now just the Minkowski metric in both diagonal blocks. That's the generalized metric. Okay, but from these two, you can immediately see that you can form some projection operators. If I just add these up, the lower block here cancels out. So I can project on the upper block, which projects on the, picks out the upper indices, and vice versa. If I take the difference, I would project on the lower, which picks out lower indices. So that means that the doubled index A, I can split canonically using these projection operators into an upper or a lower index. Okay, sometimes they're written differently with a bar overline or underline, but I will write them here as upper or lower indices. Okay, now the basic fields in this flux formulation are the generalized diffeomorphism scalars. And generalized diffeomorphisms is just the packaging together of the usual diffeomorphisms and the B field gauge transformations that occurs here. Now you can construct, from this generalized field line, you can construct scalars under these generalized diffeomorphisms. And there's a 3-index object, FABC, which is antisymmetric in its indices. It's constructed like this, antisymmetrized derivative, basically, of this generalized field line. And there's another 1-index object, which has a kind of a divergence of this generalized field line. And here I've defined this derivative with an A index to just be the coordinate index transformed to the A index via the generalized field line. Okay, and these two guys are called generalized fluxes. But all they are just the analogs of basically the spin connection and the derivative of the dilaton. So I didn't introduce this D here, but it's the generalized dilaton. It's what replaces the dilaton in this double formalism. But this guy will not really play any role in what I'm going to say. So, but basically the 3-index guy is like the doubled version of the spin connection. And generalized diffeomorphism invariance, so these are the generalized diffeomorphism scalars, and generalized diffeomorphism invariance then requires that you construct the action from these objects. Okay, but now we saw that you can project, you can use these invariant projectors to split the doubled index A into an upper or lower index. So that means that you get a number of fields from these actually. So you can have, you can make all these indices, you can project them so they're upper indices or one upper, one lower, two upper, or one upper, two lower, or lower. So you get 4 different fields from the 3-index guy, and you get 2 different ones from the 1-index flux. Okay. Now, ODD symmetry is built in here, or is manifest here. And that's because the ODD transformation rotates this M, this coordinate index, big M. But in these fluxes, that index is contracted with the ODD metric. And we're just allowed constant ODD transformations, so it's manifestly invariant under those. It's also manifestly invariant under generalized diffeomorphisms, That's why we choose to work with the generalized diffeomorphism scalars, just like we could work with this spin connection.
Excuse me,
yeah.
That I don't wait until the end of the talk, but if you have those two independent Lorentz transformation, there are some constraint imposed on them that one depends on original coordinates, the other on dual, or they depends on the both coordinates in whatever way.
We always have the section condition
on both of them.
Yeah, on everything that in the theory. Yeah, everything in the theory has to satisfy the.
But in practice, the question is one in original coordinates, the other in dual, or
no?
No.
No, if you solve the section condition, then you can make everything just depend on
one set of coordinates.
But before you solve it, everything depends on everything. Right. So ODD symmetry is manifestly built in here, and generalized diffeomorphism invariance is manifestly built in. But the price you pay is that the double Lorentz symmetry is not manifest here. So instead, these fields transform, just as the spin connection transforms in an awkward way under Lorentz transformations, this generalized fluxes transform somewhat awkwardly under the double Lorentz transformations. So I've written the transformation for two of the guys here. So these first two ones, the one with three upper indices transforms like this. So there's an antisymmetrized derivative. Okay, so if I call the parameter, there are two Lorentz transformations, right? We call them lambda plus and lambda minus before. Now I call the parameters lambda with an overline or underline. So it transforms under the overline one, but that's an antisymmetrized derivative. And then there's also some rotation of the index by this lambda. And then this guy also has this term, a derivative. Here's just the derivative of the overline parameter. And then again, the indices are rotated, and the lower indices are rotated with one factor, with one Lorentz group, and the upper indices are rotated with the other factor. Okay, so they transform, upper and lower indices here transform under different Lorentz groups. Okay, so these transformations are somewhat awkward. If you just look at the first term, it looks like this guy is roughly like a three form. Okay, it transforms like a three form, and this guy roughly transforms like a spin connection. Now, our goal is ultimately to write invariant actions, right? And normally the way we would do that is to, so the analog of this object is like the spin connection. And normally if we had the spin connection, what we would do is it's awkward to write an action, invariant action from the spin connection directly, but we know that we can construct a covariant field strength, the Riemann tensor from the spin connection. And from that, because it's transformed covariantly, we can easily construct invariant actions, okay? But the interesting thing is that approach completely fails here. For example, this 3-index flux has no independent covariant field strengths. So there's no object you could start from to build an invariant action. For example, if we take this guy with 3 upper indices, we saw that it looks like it wants to transform like a 3 form. So we would try to construct a 4-form field strength by taking an antisymmetrized derivative. But actually, because F itself is constructed out of derivatives of the generalized field bind, you find that because there's a Bianchi identity that says that this is just F squared again. So this is not an independent object. Now, if you look at the other guy, or if you look at the guy with mixed projections here, so 1 upper and 2 lower indices, for example, then we can construct something that looks a little bit like a Riemann tensor. So remember, this guy transformed a bit like a spin connection. So you'd hope to build some Riemann tensor from that. So you can take an antisymmetrized derivative in the upper index now, and then it's convenient to add these terms quadratic in the fluxes. That's not very important. Okay, so I said this is an independent object. It's a little bit like the Riemann tensor, but not quite, because it transforms non-covariantly. So if you look at how this object then transforms under the double Lorentz transformations, you find these 2 blue terms that you expect, which is just a rotation of the indices by the 2 different Lorentz factors. But then you find these pieces, which is F times d lambda and one with the other Lorentz factor. And those should not be there to transform covariantly. Okay, so this object is not quite covariant. But if you just work to lowest order, so you notice here that there's no, before in the Fs, we had just a d lambda term. Here, there's no d lambda term. Every term is proportional to F or a derivative of F. And there's no term just proportional to lambda. So if you work to lowest order in fields, this R is actually invariant. So that makes it a useful object to work with. You can start from that and then try to improve it somehow. Okay. Now, if you, of course, you can go back from this double formulation. You can gauge fix the double Lorentz transformations. You can set these two independent field lines that we had equal to each other. Then you just have one copy of the Lorentz group left. And then you go back to the usual supergravity fields. And if you do that, you can derive what the relation is between these generalized fluxes and the ordinary fields. And if you do that, you find that this flux with the one upper and two lower indices, for example, is basically the spin connection. It's not quite the spin connection. It's a torsionful spin connection. So it's the spin connection shifted by the field strength of B. Okay. Similarly, the other guy with one lower and two upper indices is omega plus, where I put a plus sign here. Okay, so from that, you can plug that into this definition of this curly R, this sort of double Riemann tensor. And what you find is that what it becomes is the field strength of this torsionful connection, which I call R minus. So that's the Riemann tensor for this torsionful connection. But then it also has two pieces. It has one piece, which is quadratic in the spin connection. And so from here, it's manifest that it doesn't transform covariantly. Okay, going the other way, we can express, obviously from this equation, we're going to express instead R minus, the usual Riemann tensor in terms of this R, this curly R, and we can go backwards and write the spin connection in terms of these, this generalized flux. And if you do that, you get an expression like this. Okay, but the problem is that this last term does not transform nicely under ODD. In fact, it manifestly breaks ODD, or rather I should say double Lorentz transformations, because we replaced ODD here by double Lorentz transformations. So this term manifestly breaks the double Lorentz symmetry. And that's because the upper and lower index is contracted here. So the E is a lower index here and an upper index here. But they're completely different in this formulation. Then they transform with the two different Lorentz groups. So just contracting them like this is does not respect the double Lorentz invariance. The only way to respect the double Lorentz invariance is if you contract indices with eta. So for example, if you have a thing like this, if you contract E and F with an eta, that respects the double Lorentz transformation because E and F are lower indices and they transform with the same Lorentz factor. Okay, so those are the only things that respect double Lorentz transformations, whereas this guy does not. Okay, said another way, that means that this object cannot be a nice, it's almost a nice object under ODD, but not quite. Okay, so what does all this mean for the quartic Riemann terms and the effective action for the string? Well, let's go back to what is known about them. So their form is known for, if you just look at just the pieces involving the metric. So if I set the B field and dilaton to 0, it's known that they take this form. So as we said, they're proportional to zeta 3. But as Olaf mentioned also in his talk, there's this structure T8, T8, R to the 4th, and then there's another term, epsilon 8, R to the 4th. They appear in this combination. This was derived from scattering amplitudes in the 80s, starting with Gross and Witten, the first term. And then there was a bunch of other papers. So let's look a little bit in detail how these are defined. So this epsilon 8 term is defined by taking two 10-dimensional epsilon tensors, and you contract two indices, C and D here. And then you get something which has, if I write the indices lower on one and upper on the other one, then I have 8 lower and 8 upper indices. And I contract them with the 8 upper or lower indices that you have on a product of 4 Riemann tensors. Okay, in this way. So that's how the second term is defined. In the first term, you have this T8 tensor structure. This T8 tensor is defined in this way. It has 8 indices. And if you contract it with 4 antisymmetric matrices, M1, 2, 3, and 4, then the contraction is defined to give you 8 times the trace minus twice the product of these two traces, and then plus the cyclic permutations of the last 3. Okay, that's just the definition. This comes out of a scattering amplitudes. And then here, of course, you take one T8 and contract with all the lower indices, so B1 through B8, and then you take the other one and contract with all the upper indices. And that's how the first term is defined. And this first term, you can write as something ODD invariant at the leading order. If I just look at the quartic order in fields, by simply, basically by using this, if I said H to 0, this is just the Riemann tensor. And to leading order, this transforms like a nice thing. I can forget this quadratic guy that doesn't transform nicely. And so at the leading order, this is fine under ODD. But if you look at this other guy, this epsilon 8 guy, that involves explicitly contractions between upper and lower indices. And there's no way that I can rewrite it in terms of this, this curly R. I mean, at the lowest order, that's the Riemann tensor and this curly sort of double Riemann tensor are basically the same. There's no way that I can write these terms without having contractions directly between upper and lower indices. And as we said, such contractions are not allowed. They're not compatible with double Lorentz symmetry. But this problem is actually also at the next order, because as I think Olaf also mentioned, this term, if you just look at only the quartic term here, then you replace R by just D of the spin connection. And then this term is a total derivative because you see it's anti-symmetrized in, for example, all these lower indices. Okay, so the purely quartic term here, if you expand it out, is a total derivative, so you can throw it away. So this problem appears only at the next order. Explicitly, you can rewrite, you can throw the total derivative away, and then you can rewrite this R to the 4th, epsilon 8, R to the 4th as epsilon 9, 2 spin connections times R cubed. Okay, with this, yeah, you can show with some coefficient. So you see that this is 5th order in fields. So the problems appear at the next order, not at the quartic order, but at the 5th order. But if you make a careful analysis, as we did, at the 5th order in fields, you find that there's no expression which is ODD invariant that captures these terms, okay, modulo some mild assumptions. Or O1010 invariant, to be explicit, in 10 dimensions. Okay, so that's a problem if you want to, I mean, that seems like you cannot describe then this correction in the double field theory language. But we know that we must still have the ODD symmetry. It must still appear on dimensional reduction, okay? So we should still be able to use that to fix the form of this, this correction, even if we can't do the simpler trick of using double field theory. Okay, so we have to look at the dimensional reduction. And it's convenient to do it actually, to continue to use this language of double field theory because it packages the fields naturally in a way that transforms nicely under ODD. So we'll look at how you dimensionally reduce in this double field theory language, and it's quite simple. You can write so the boldface here means the higher dimensional object, and you can reduce the way you reduce the generalized field bind is this. I have this guy, and then I have to add some kind of rotation by this 1 plus u, where this E is very simple. It's just diagonal. It contains an external generalized field bind, and then it has the internal ones. So primed coordinates will be the internal ones. Okay, and it's only for the internal ones that I care about the ODD symmetry, right? Because I only have ODD for the internal coordinates when I dimensionally reduce. Then I can package the vectors, so the Kaluza-Klein vectors together with the vectors coming from the B field into one ODD vector gauge field with this doubled internal n index. And if I do that, the non-zero components of this U, there's not many, and they just take this form. It's not, the precise form is not very important. It's just to say that it's relatively simple to dimensionally reduce in this language. But let me simplify a little bit more by just setting all the scalars to 0. So this purely internal generalized field bind will contain scalars from the dimensional reduction, but I'll set them to 0 in the following because it simplifies things, and it turns out to be enough to do that. And then you can look at what this 3-index generalized flux becomes. And if you take 3 external indices, you just get the corresponding thing. But if you take 1 internal and 2 external indices, it reduces, this 3-index object reduces precisely to the field strength of this double gauge vector field, okay? So this F with 1 primed and 2 unprimed indices is the field strength of this double gauge field from dimensional reduction. Okay. And now we can express, so we want to write an action in 10 dimensions in terms of, I set the dilatones to 0, so all scalars will be 0. So I want to write an action in terms of H and the Riemann tensor, but I'll work with this Riemann tensor computed from this torsionful connection because it behaves more nicely. Okay, so I want to write an action in terms of those objects, but it's convenient then to express those objects in terms of the generalized fluxes, and you can do that this way, and this expression we saw before. And then to dimensionally reduce that expression, because then we can immediately basically read off the dimensional reduction of that. For example, for this R, we find that if you take all the indices to be external, we get just the Riemann tensor. Sorry, not just the Riemann tensor, you get this R ABCD, which is written out here. It's just the usual Riemann tensor with the distortionful, computed from distortionful connection, plus some pieces quadratic in this F. But notice that the primed indices are contracted with etas here. Okay, so they're compatible with the doubled Lorentz transformation of these internal indices. Okay, and for these guys with 1 primed index, you also get something which is compatible with that symmetry. But then you have this red piece, delta ABC, which comes from this problematic term, which takes this form, where I now take this E index that's directly contracted here to be an internal index, which is the one that should transform under ODD. Sorry, under the double Lorentz transformations associated to the internal indices, which is what replaces ODD. And as we said before, a direct contraction like that doesn't respect ODD because they transform with different factors of the internal double Lorentz transformation. So this is a problematic term that doesn't respect ODD. Okay, and now we start from an ansatz for the 10-dimensional action, and then we reduce it, and we require that the terms that don't respect ODD, like the ones coming here, should cancel out. Okay, and we start from an ansatz that's inspired from what we know. So we have the T8 R to the 4th. I'll generalize it a little bit by including in this r to the fourth, also some things quadratic in H, which have the same structure. It turns out to be useful. So I put a coefficient A and B here, some things quadratic in H. And then here you see that I wrote epsilon 9, some f squared r cubed. So I removed the total derivative piece to explicitly show that this term is of fifth order in fields. And this f squared, so explicitly, this term stands for this. So there's two contracted epsilon tensors. Then this f squared combination, remember these f's are basically the spin connection. So this gives some spin connection square term. And if you add a total derivative, this gives you the extra Riemann term and gives you back Riemann to the fourth. And then also here, and I put a coefficient C there that we want to fix. And then also here I added in terms of similar structure, but just involving H. It's because I can, and it turns out to be important to allow that. Okay, the details are not super important here. And then the idea is the following. So now we perform the dimensional reduction of this ansatz using the expressions that we derived for the dimensionally reduced fields. And then we demand that the non-invariant terms should just cancel out and we should be left with something ODD invariant. But to simplify the calculations further, because this turns out to be quite complicated, as we already did, we set all the scalars to 0, including the dilaton. We'll restrict ourselves to work only up to the fifth order in fields as well. We'll use equations of motion in the reduced theory, which means we allow field redefinitions in the reduced theory. And we'll focus on the terms that are, the non-invariant terms that are quadratic in the double gauge field strength. There are also terms that are quartic in the gauge field strength, but they will cancel in a similar way. In fact, they're less constrained than the ones quadratic. And it turns out that this is enough to fix all the terms, modulo, of course, the dilaton terms, because we set the dilaton to 0. And it's convenient to organize the calculation by the power of H that appears. So at 0th order, so the terms that don't involve the B field at all, and which don't respect the ODD invariance. And what I really mean every time I say ODD invariance in this language, what I really mean is the double Lorentz invariance, because we traded the ODD invariance for the double Lorentz invariance. The terms that don't respect the double Lorentz invariance, because again, they have an upper and a lower primed index contracted, look like this. So from the T8 R to the 4 term, you get this. And from the other term, you get this. Okay? And there's no way, because these have a completely different structure, there's no way they can cancel against each other. In fact, this F with a lower primed index and an upper primed index are different fields, right? Remember, one is built, roughly one comes from the Kaluza-Klein vectors and one comes from the vectors of the B field. So they're not the same. So the only way that this can cancel out is actually if this combination of two Fs is such that it's anti-symmetric under exchanging the two pairs of external indices here, AB and CD. So if the FF terms are such that FF ABCD is minus FF CD AB, then this expression and that expression vanishes because the Riemann tensor has a symmetry under exchanging these pairs of terms. So R ABCD is equal to R CD AB, which means that these cubic terms in the Riemann tensor inherit that symmetry. And then if you contract it with something that's antisymmetric, it will give you 0. Okay, so that's the only way that these terms can go away. And that fixes these coefficients. In particular, you see that it fixes A to be minus 1/2. This B term has a different structure and has to be 0. And then finally, it fixes D in terms of C and E. And then we go to the first order in H. Here you find that it's actually not possible for the non-invariant terms to cancel unless you add something more to the 10-dimensional Lagrangian. What you have to add are terms of a form H squared R cubed. Specifically, it turns out that you can cast them in this form. It's important here there's no contraction between these two H's. So that actually means that it doesn't mess up the result at 0th order in H. In fact, the need for terms like that was already seen in scattering amplitude calculations by Liu and Minesi in 2019. But they didn't write them in such a simple form. And additionally, at this order, you find that the remaining coefficients that I had are fixed. You find the C is 1/5, D is 1/2, and E is -1/2. Then at the quadratic order in H, it gets more complicated. And again, you find that the non-covariant terms cannot cancel unless you add terms now of the form H squared and DH squared times R to the 10-dimensional action. And the form of these terms is very non-unique because you can partially integrate in many ways, and you can use Bianchi identities, so they're kind of hard to nail down. But one way of writing the required terms is like this. You can split it into 3 pieces, call them L1, L2, and L3. Just for completeness, I've given them here, though the expressions are quite long. And this L1 consists of things where there is a contraction between these 2 H's or between the 2 H's under derivatives. Okay, the exact form is not important. L2 is slightly longer. It consists of terms where there's no contraction between these 2 H's or between the 2 H's under derivatives. Okay, but what's important in both these is that there's an antisymmetrization in the indices on the derivatives and 2 indices on R, which allows you to partially integrate these terms and write the dimensionally reduced terms in a specific form. I don't have time to explain exactly why, but all these have an antisymmetrization for a very good reason. And then there are 2 terms that cannot be written in that antisymmetrized form, and they're these 2 guys. Okay, the form of these terms is not very important. This is not probably the final expression for these terms, but the total of terms is 41. And this should be compared to the only other expression known for these terms, which is from the paper of Garossi, which consists of 106 terms. So there's some simplification there at least. So what have we done? Well, we managed to fix the completion of R to the 4th up to terms of 6th order and dilaton terms by requiring ODD symmetry of the reduced theory. The remaining terms to fix are these types. So there's H4th R squared, H6 R, DH squared H to the 4th and H to the 8th plus dilaton terms. They're expected to be somewhat simpler, but they still require some work to fix them. So let me conclude. It doesn't seem possible to write the alpha prime cube terms in an O1010 invariant form before you dimensionally reduce, as you would like to do in double field theory. But you can fix their form by requiring ODD symmetry of the reduction to 10 minus D dimensions. That should be possible. Or that symmetry has to be there, and it seems like it completely fixes the result. But it requires a surprisingly complicated form of the B-field couplings, as we saw. And the ODD symmetry is realized through some very intricate cancellations between these different terms, these different non-invariant terms. And what remains to be done is to fix the 6th, 7th, and 8th order terms and the dilaton couplings, which is certainly possible. It requires a little bit of work. But what's more interesting is maybe if we can make the ODD symmetry more manifest in some way. And perhaps the way to do that is to give up the manifest Lorentz invariance in 10 dimensions, but I don't know. And another interesting question is whether we can fix also the Riemann couplings. So far, I just talked about the NS and S couplings, but can we fix the Riemann couplings by using S duality? So SL2R, SL2C for the type 2B string. Okay, that's it. Thank you.
Thank you. So I have 2 questions. The first one is about scheme dependence of alpha prime calculations. Normally, is it expected that the effective action, even expanded in alpha prime, is scheme dependent? And if yes, can we choose a scheme in which the ODD become invariant?
Yeah, of course it's scheme dependent, right? So you can make field redefinition. I mean, that's just the freedom to make field redefinitions that involve alpha prime in the higher dimensional
But this can help, you know, in obtaining ODD.
Yes. So, but what I'm doing here is it's basically picking a scheme that's adapted to ODD, because I'm starting from the double field theory. Well, sort of anyway. I'm starting as much as possible. I'm using the double field theory field, so these generalized fluxes and so on. And so they come with a natural scheme that's adapted to the ODD transformations.
So you believe it that this is the best scheme, or you can prove it that it is the best scheme?
No, I can't prove it, but I suspect that if I can make it look as O1010 invariant as possible in 10 dimensions, then it should be that should make it maximally easy to see the ODD invariance when I reduce. I mean,
the second question is much related to the last comment about Riemann. You know, when you reduce, so some fields will cease to be, let's say, stringy fields like gravitational B field, they will become a gauge field. And is it possible that in 10 dimension, adding some gauge fields, which would be some composite of Riemann fields, would cure the situation? You know what I mean? Because if you get down by dimension, then you obtain ODD invariant expression, right? Because you have more fields.
Yeah.
And perhaps in 10 dimension, those more fields can come from Riemann. You see?
Right, but there's no problem with ODD invariance just for the NSNS sector. I mean, it's only in the NSNS sector where it's
this. You say that in alpha prime cube, you cannot organize those fields in something which would be ODD invariant.
Right. Sorry, there are two Ds. It's confusing. So O1010, you can't make it O1010 invariant in 10 dimensions. So before dimensional reduction. And I don't see how including Riemann fields can affect that conclusion.
I see.
You can make it ODD invariant when you reduce from 10 to 10 minus D dimensions.
At third order of alpha prime.
That will be true.
At third order of alpha prime?
Sorry?
You can do it at third order?
At third order in alpha prime, yeah.
I see.
Yeah. If provided you add the specific term, I mean, it fixes the result in 10 dimensions.
Hi, we have a question from Zoom from Falk. So Falk, did you?
Okay.
Hey, Linus. So nice talk. So I wanted to ask you, when you say dimensional reduction, so you mean on a torus, correct?
Yeah, I mean taking the fields independent of that number of spatial coordinates, basically. Yeah. So whether it's a torus or not, it doesn't really matter. Like in Olaf's talk. Right?
Okay, but have you thought about
independent of D coordinates?
Yeah. So, but have you thought about doing more general dimensional reduction with something like a generalized Schurk-Schwarz ansatz?
I don't know how you would see the ODD symmetry there.
I mean, at the leading order, you see it, right? So this is what you can do. I mean, you can do. I mean, this was one of the really surprising results of double field theory, that you can do this generalized Schurk-Schwarz reductions.
Right.
And you still get something which are spheres, or I mean, which are not tori. So, and I mean, it would be curious to see whether something goes wrong there and whether one can really pinpoint what goes wrong. And I mean, it's very similar to what you have done, but that gauge fields become non-abelian, right? So you are working with abelian field strengths and gauge fields.
Right.
But so in this case, they would become non-abelian, and whether there is still some magic that cancels things, or whether you can pinpoint that you have to be abelian.
Okay, yeah, you say as another way of checking this obstruction that we find in 10 dimensions, you could try to reduce on something other than a torus and see if you can get rid of this obstruction. I haven't thought about it. In principle, you can try.
Yeah, okay, thanks.
I was just wondering about the calculation. So you made a certain ansatz in 10 dimensions, right?
Right.
And is it clear that this is sort of the most general? I mean, is it possible that you haven't got the kind of unique thing that will give you this ODD invariance upon reducing?
What are you asking about the result? I mean, are you asking about deriving this result, fixing the form of the terms in 10 dimensions?
Yeah. So you kind of start from some ansatz and then you fix the coefficients. And is it possible that there could be a more general ansatz that would still do?
Of course, this is not, I started from this, which is not the most general ansatz. In fact, I saw that I needed to add other terms to make it invariant. So are you asking, I mean, this calculation, the calculation that I did doesn't prove that the result is uniquely fixed, but the calculation of Garussi proves that it's uniquely fixed by just T-duality on a circle. So I don't really need to prove that again.
Sure. And were you able to check that, your result is the same as this?
As his, no, I have not done that. It's very complicated to do it because, I mean, even if you, he computes all the terms, all the NS and S terms, but even if you just focus on the ones that I computed, there's a lot of terms, and it's also the fact that you can make field redefinitions. I mean, you're going to have to make a bunch of field redefinitions to match the results, and it's very complicated to match them.
Sure.
They have to match, but it's complicated to check.
Thanks.
A sort of more conceptual question about the O10 invariance. Just out of curiosity, what's the kind of motivation for expecting it to be there? Other than is there a deeper motivation for why you might think it's there?
I'm not the right person to ask that.
Okay,
but I mean, I haven't heard of a convincing argument, to me at least, that it has to be there to any order in alpha prime.
And is there something that it not being there kind of obstructs some kind of ideas or some kind of mechanisms that it would obstruct, or is it?
Well, it's a problem for double field theory, right? If you want a double field theory that works to all orders in alpha prime, this is saying that that doesn't work. But there could be some way around that. I haven't proven conclusively that you cannot come up with some double field theory formulation that works also at the cubic order in alpha prime. From my point of view, it's more, the question is more, why would you expect that? Just like your question. From my point of view, we have no right to demand 10 invariance in 10 dimensions. So I'm not surprised that it doesn't work to all orders in alpha prime, but other people might be of different opinion.
Well, maybe Falk, you have a question, Falk?
Yes, I mean, I want to also make a comment to this question. I mean, I think so. What Linus says is right, because for general backgrounds, there should not be something like O10. So, I mean, it should be connected in some way to duality. So, and I mean, you would expect some kind of dissymmetries when you expect that dualities don't break down under alpha prime corrections. So, and I mean, one reason why I really would hope that some structure is there, and so that's why I also was asking about the generalized, the generalized Schwartz transformation, is because when you want to have Poisson-Lie T-duality not breaking down at higher orders of alpha prime, you need some kind of this formulation. And I mean, it works remarkably well, for example, for the leading order alpha prime corrections. And I mean, there's also this connection to integrability, right? So, I mean, you would really hope that these kind of dualities and probably even their connection to integrability gives you something about calculating alpha prime corrections to arbitrary high orders. So, and that's why I think there is some structure which you could find, but of course the question is what is the structure, and is this probably more than ODD or what is it?
I would also like to ask a question.
Sure.
So some of these low energy constants are known to all orders in G string. There was this modular forms and so on.
Right.
What role does ODD play there?
So ODD, I think I maybe briefly mentioned at some point. No, I think it was here. Yeah, so for example, the situation is a little bit funny because the terms, these are to the fourth terms for the type 2b string, basically because of the S duality, they look the same at one loop, right? So they also take this form at one loop. Actually, for type 2A, there's a different sign here. But for type 2B, they take the same form. But what's funny is that when completing them, we found these terms, these h squared r cubed terms. They have to be there because of ODD, but they're not there in the one loop result. So it's a different, the one loop result has a different completion of the same r to the fourth terms. So ODD is not there, at least not in this way, at higher loop orders. Yeah.
Any other questions to Linus? Well, then let's thank him again for a very nice talk.